Good afternoon. Can you please take your seats? I would like to welcome you to the medal lecture of the Alfred Wegener Medal. And it's my great pleasure to introduce to you Edouard Barr, this year recipient of this medal lecture. Edouard Barr will, in a minute, give his presentation. I just very briefly would like to give you an impression about his standing in the field. Of course, a 1-minute explanation can only give a glimpse of his standing. Edouard Barr is a professor at the Collège de France in Paris for climate and ocean evolution, and he's also an associate director of CEREGE, which is the French Center of Environmental Geoscience. He has already received many distinctions, including membership of the French Academy of Sciences and the Belgian Academy of Sciences, and a wide range of other awards and other distinctions. Professor Barr has published extensively with more than 10,000 citations, 200 publications in the top journals we have in our disciplines, including Nature and Science. And he's one of the, I can say, one of the best known and most distinguished people we have in the field today. And it's my great pleasure to welcome Edouard Barr to the stage to deliver his keynote address. Please.
Mr. President, thank you for this generous presentation and citation. I mean, it's an extreme honor for me to be here, obviously for the Wegener Medal. And I have prepared a few minutes of speech for explaining and acknowledging and thanking, in fact, the colleagues and friends who helped me to be here. But I reserve that for tonight, for the award ceremony. Today, my task is, right now, my task is to entertain you with some science. So I will try to do that and to clarify, maybe for some of you, the title that I have chosen for this talk, The 3 Lost Millennia of the Last Deglaciation. I will try to clarify that. So I'm starting with Alfred Wegener. Alfred Wegener is mostly known, in fact, for his theory of the continental drift. But he was also, and we have to remember that he was also a fine meteorologist, and also he did the groundwork on polar research. And just as an illustration of that, I'm showing to you here one of his map of the Pangea during the Carboniferous, where you can see that he was not only drawing, in fact, the different continents, but also he was showing on the map the deposits that were corresponding to ancient ice sheets, tillits, so ancient moraines, and also desert deposits such as salt deposits and gypsum. So clearly, he was very much interested also by the climatology. In fact, this work he did also in collaboration with his father-in-law, Vladimir Köppen, who was also a fine scholar of the time, a distinguished meteorologist, and a pioneer in the relationship between plants and climate. And Vladimir Köppen is also well known for the first comprehensive map of the modern climatic zones that is still being used today. So I just picked this graph from the FAO, and it's still used almost unchanged since that time. So Vladimir Köppen collaborated a lot with Wegener. And they were friends, both of these scholars were friends, in fact, with one of my other heroes in science, Milutin Milenkovic, who is well known, in fact, for his complete formulation of the astronomical theory of climate change. So this is a graph showing, in fact, a picture of the changes of the orbital parameters. So on the lower part of the panel, and on the upper part, you have the calculation, this early calculation over the last 650,000 years of the insolation curve at 55, 60, and 65 north of latitude. the location of the former ice sheets during the glacial periods. And I mean, just as a parenthesis, I have to stress that Milenkovic was a mathematician and a physicist, and this is the reason why he was, right at that time, showing, in fact, the progression of time from left to right, and as many geologists are doing exactly the contrary, so to make things simple, because sometimes you can't see, in fact, the numbers. I always put an arrow just to show you, to indicate the progression of time from left to right in that case, and you will see that sometimes it's the reverse. So this early publication was, in fact, in the book by Köppen and Wegener, which, again, stress the importance of the Milenkovic theory in the connection with paleoclimatology and what Wegener did in the past. So Milenkovic, in fact, understood the configuration that were leading to ice sheet growth during glaciation, and also the decay of ice sheets, especially since the last glacial period, the deglaciation that I'm interested in during this talk. So he understood, and this, the main features of the configuration that led, in fact, to the decay of the ice sheets since the last glacial maximum are represented and simplified on that graph, where you can see that in order to make, to melt, in fact, the former ice sheets, you have to have a minimal distance during the summer solstice, and at the same time to have a large value for the obliquity, a large tilt, in fact, to explain the summer melting. So this is the configuration that was understood as early as Milenkovic's work. And it's still today, we know that the main pacemaker of the ice ages and the small impetus for the deglaciation is linked to this orbital theory of paleoclimate. And because we are speaking about the glacial period, I would like also to set the scene by showing to you what was the glacial world about 21,000 years before present. And I'm showing here, in fact, the original climate map that was drawn, in fact, in the late 70s and early 80s. And I still use it because it's still unsurpassed in terms of artistic quality. And at the same time, the big picture is still there. In fact, we can see this is the northern hemisphere during the glacial maximum. We can see very clearly, in fact, the Laurentide ice sheet that was sitting on top of Canada. We can see also on northern Europe the Fennoscandian ice sheet. And obviously, there were major changes of climate. We can see that it was possible, because of sea level drop, it was possible to walk from Siberia to Alaska through the Bering Strait. It was possible to walk from England to France. And we can see, as the gray zone represented on that graph, that there was a lot of more of sea ice at that time. Something that I will come back to later in the talk, which is quite important right at the start. And in the 80s, this map was called the 18K map, because people thought that the glacial maximum was corresponding to 18,000 years before present. And we know now that it's no longer true. And, but this is, again, just as a simplification and just to set the scene, how the last deglaciation was looking like in the 80s, in the early 80s and late 70s. People thought that the global sea level was rising very smoothly over the last deglaciation, and with almost a sigmoid shape based on the global delta O18 measured in benthic foramifera, and more or less this deglaciation was corresponding, in fact, to the maximum of the 65 North summer insolation, which is represented on the second panel. And later, in the mid-80s and late 80s, came the fact that with the bubbles in ice cores, in Antarctica ice cores, we know there were measurements of atmospheric pCO2, so we already at that time we learned that there was another forcing during the last deglaciation that could explain, in fact, this big climatic transition, which is the atmospheric pCO2 that rose by 100 ppm, which added, in fact, a significant radiative forcing. And so this was more or less what the last deglaciation was looking like when I started, in fact, my PhD. And then, over the last 20 or 30 years, there was a lot of progresses on different fronts. So it's not possible to review and extensively and exhaustively all the facts that have been added, but I will try to make clear a few things that really dramatically change, in fact, our view about the last deglaciation. One of the first things that we learned, in fact, especially from the study of corals that were drilled offshore different islands in the tropics, for example, at Tahiti. This is the work that we did offshore by drilling onshore and offshore Tahiti in the frame of IODP. We learned, in fact, that the last deglaciation was an enormous change of sea level by more than 120 meters. But at the same time, we also learned that it was not a smooth curve, that there were acceleration, especially what is quoted as what is referred as the Meltotopus 1A, that is a dramatic rise of sea level by tens of millimeters per year during a time period in the middle of the last deglaciation. Actually, we knew about this Meltotopus 1A even earlier than the work that we did at Tahiti. We learned about that with a similar work that we did in collaboration with Rick Fairbanks, that I did in collaboration with Rick Fairbanks when I was working at Lamont Doherty in New York. And at that time, Rick Fairbanks drilled the coral reefs offshore Barbados. And he published in 1989, a sea level curve that was showing, in fact, these rapid rises during the last deglaciation based on carbon-14, especially the Meltotopus 1A. But then my task had been to complement, in fact, the work by using uranium-thorium by mass spectrometry, and the outcome, the main outcome of the work, which was published, as you can see on that graph, because that's directly from the original publication that was published in 1990. The sea level was, again, rising very rapidly with the uranium-thorium that is more accurate and more precise. So we had a confirmation about the fact that the last deglaciation was a very unsmooth process, very irregular process. But at the same time, one key information was that the last glacial maximum was much older, had to be shifted by 3,000 years. In fact, the last glacial maximum can be seen with the corals that are about 120 meters, and they are dated with the carbon-14 at 18K, so very much in agreement with what we knew about the 18K map. But with uranium-thorium, that is more accurate, we were able, in fact, to prove that, in fact, the LGM had to be shifted by 3 kiloyears up to 21K. So this came directly from the corals. And the corals, in addition to tree rings, to information on speleothems, on varved sediments from the ocean and from lakes, have been used, in fact, in the frame of an international program that is called the ANCAL program, in which we regularly update, in fact, the calibration of C14. We use, in fact, the comparison between carbon-14 and other means, accurate means of chronometry, to relate carbon-14 and true age, calendar ages. And this is just a summary graph that is showing, in fact, the latest two calibration curve, ANCAL 04. We started, in fact, the process since '93. The next iteration of the ANCAL curve will be released at the end of the year. It will be called ANCAL 13. But just on that graph, which is showing, in fact, the time period of the last deglaciation, I represented, in fact, the two calibration, ANCAL 04 and ANCAL 09. And as you can see, there are a few details that have been changed. I also represented some additional data that we have on the thing. But the main big picture is still there. We can see, for example, that 18K in C14 since 1990, since more than 20 years, is still corresponding to 21K in calendar age. And what we can see also is that over most of the deglaciation, everything had to be shifted by 3,000 years. So this is more or less explaining the title of the talk, but you will see that there is more in these 3 millennia also. So what happened during this extended time period of the last deglaciation? This will be the other part of the lecture. I will, in the late 80s, the main problem was to date paleoclimatic archives. And in addition to mass spectrometry of uranium-thorium, what was really a revolution for us was the development of accelerator mass spectrometry, especially of carbon-14. And this, just to illustrate the thing, I'm showing to you one of the earliest dated deep-sea sediment record dated by accelerator mass spectrometry directly on the same foraminifera that were used, in fact, for measuring temperatures. For example, here you have two curves. You have the upper curve that is representing the delta O18 measured in planktonic foraminifera, and the lower curve is showing versus depth in that case, but you have the ages on top of on the top of the graph. It is showing, in fact, the temperatures that are inferred from the faunal transfer function. So it's based on foraminifera, and in the last deglaciation, at least on that site, which was for that core that was collected off Portugal, it was clear that the last deglaciation was not a smooth process between the glacial maximum and the Holocene. What we evidence, in fact, with those well-dated sediment is that there were many drops of the temperature, especially one that was already well known on the continent, which is called the Younger Dryas. And at that time, we evidenced another one, which we know now is corresponding to the so-called Heinrich 1 event. Actually, this was published, in fact, before the work of Hartmut Heinrich. And even at that time, in fact, we attributed, in fact, this massive drop, which lasted, in fact, 3,000 years. This massive drop to a pulse-like injection of icebergs in the Atlantic. And later, a year later, and then there was a decade of work to identify that this Heinrich 1 was not isolated. It was a regular aspect of the behavior of the Laurentide ice sheet during the glacial period to lose part of its mass as dramatic events of release of icebergs that are schematized, in fact, on that graph, where you can see that the Laurentide was losing icebergs coming out from the Labrador Sea, and they were melting in the North Atlantic all the way, and melting and going all the way to the other side of the Atlantic, where we had the core of Portugal. So it's a massive amount of meltwater that was released in the Atlantic, and of course it affected the convection and the density, because the fresh water added in the North Atlantic has an effect on the circulation. But at the same time, for the geologists, it is interesting, and this is the reason why Hartmut Heinrich did his career on that aspect. They are releasing, the icebergs are loaded with ice-rafted debris, and it was possible, in fact, to count and map them in the North Atlantic. And of course, close to the ice sheet, close to the Laurentide ice sheet and the Labrador Sea, the IRDs are apparent. The Heinrich layers are big layers. Whereas on the opposite side of the Atlantic, in fact, we only add a few grains, but they are there. In fact, we went back, just as an illustration, so it's one core among many, but more than 10 years later, we went back, actually 12 years later, we went back to the same core of Portugal, and we confirmed, in fact, we remeasured, in fact, the sea surface temperature with another technique that is based on the Alkenon thermometry, and basically it confirmed, in fact, what we had with the foraminifera. But at the same time, we also added the counting of the IRDs. And in that case, we are very far from the source, but they are there. And what was also quite interesting, there was an interesting aspect, is that the Heinrich layer was double. In fact, it was not a single event. We had two main phases that we named H1A and H1B based on the IRD counts and also based on the magnetic susceptibility. And in the same core, and in other cores from the North Atlantic, other colleagues have also documented the variation of the deep water circulation based on proxies that are helping us to quantify, in fact, the deep sea circulation that is linked, in fact, to this problem of freshwater input. And I don't have time, in fact, to describe the proxies, but this is shown on the lower graph with this deep water ventilation index that is based on the protactinium to thorium ratio. And what we can see, and this has been confirmed by many other tracers different from the protactinium thorium, during Heinrich 1, there was a massive drop of the circulation, of the deep sea circulation in the North Atlantic, not only at that site. So this is this was a confirmation, and obviously this is one core. And in order to understand the last deglaciation, we need many of those. And this is what we did actually with other colleagues. In fact, several colleagues had the same idea, but we did that in collaboration with Jeremy Shakun and colleagues from the US to map and to make a synthesis of the last deglaciation by taking sedimentation records that were highly dated. With accurate dating. So this is a map showing where the sites were collected. And the different colors correspond to the different climatic proxies that were used, in fact, to reconstruct the paleotemperatures. And there are geochemical ones and other ones. And at the same time, what you can see, which is very important, is that in order to understand, and I will illustrate that in a minute, in order to understand mechanistically what happened during the last glaciation, we need, in fact, to map that globally at the different latitudes. And as you can see, you have cores here that are coming from Antarctica, the Antarctica ice cores. You have also cores from Greenland. I should have included many spots. And very important also are the fact that we had a lot of deep sea records that were collected in the tropics. So just for the sake of illustration, I'm showing here just from a work that we published some time ago based on Alkenon thermometry, the comparison between the three records that were included in this Shakun et al. Recent synthesis of the last deglaciation. You have on the top of it a well-dated tropical Indian Ocean record of temperature, and you have the famous Greenland and Antarctica ice core record that can be compared very precisely. And you can see from that point that there are differences between the record. But in order, in fact, to study more precisely the differences, we were obliged, and this was done in the frame of the work by Shakun, to calculate averages, and in order to understand what was going on, to calculate averages for the different latitudinal bands. So I'm showing here to you one of the major figures of the work by Shakun et al. And in that case, the age is progressing from left to right, as Milenkovic did, instead of from right to left, as all geologists are used to do. But you can recognize where we are. So what is important on that graph is a representation of the average temperature rise during the last deglaciation at different latitudes. And what we can see is that the different latitudes are very different, especially when we compare the latitudes in the southern hemisphere and the northern hemisphere. What is also quite clear is that the earliest sign of warming occurred, in fact, in the high latitudes between 60 north and 90 north, which is quite logical according to the orbital theory, because this is where the primary insolation change is occurring. But very soon in the northern hemisphere, not only in the North Atlantic, but in the whole northern hemisphere, we can see that there is a drop of temperature during these 3,000 years, corresponding to the Heinrich 1 event. And which explains that the northern hemisphere is significantly delayed with respect to what is happening in the southern hemisphere that is more simple. What you can see is that the rise of temperature in the southern hemisphere, especially between 60 and 90 south, is rising quite rapidly, starting at 18,000 years before present. And it's more or less also corresponding to the rise of the CO2 that is escaping from the Southern Ocean. So we have an additional kick and an additional forcing that is explaining, in fact, this rise of temperature. But what is significant also is the delay by 3,000 years that we observe in the Northern Hemisphere. A way to even simplify it more, but to understand it a bit better, is to go even one step further in the simplification. So instead of calculating a global mean temperature, just to separate the northern hemisphere from the southern hemisphere, and this is what was done again in the frame of the work by Shakun et al., where you have on the top of this panel, the southern hemisphere, the weighted mean, in fact, of the southern hemisphere rise of temperature over the last glaciation, and is plotted also in blue, the northern hemisphere temperature rise, which is significantly delayed. And what is interesting is also to calculate the direct difference, the residual, I mean, the difference between the two hemispheres, which is shown as the purple curve. And the purple curve is showing a very distinctive W shape with two minima that are corresponding more or less to the H1 and the Younger Dryas event. I mean, two minima, meaning that, that there is a significant difference between the southern hemisphere and the northern hemisphere. And again, the fact that this curve of the difference between the northern hemisphere and the southern hemisphere corresponds quite accurately with what we know about the changes of the Atlantic meridional overturning circulation with the proxy, for example, of protactinium to thorium, shows that mechanistically the two are probably linked. I mean, I don't want to summarize, in fact, here, I don't have the time, but there are many more evidence based on protactinium data, based on other proxies, C13, neodymium isotopes, and so forth. But clearly, we have a mechanistic link between the two. And the mechanistic link is, in fact, the deep sea circulation. Again, this overturning meridional circulation that is represented and sometimes oversimplified as a conveyor belt, the conveyor belt of Wally-Breuker. And this is which is on the top of the graph. And you have a more realistic picture taking into account what we know about oceanography that was published more recently. But for the Atlantic, the main big picture is that there is a northward flow from south to north in the Atlantic, and a sinking in the North Atlantic, in the Nordic seas, and also in the Labrador Sea, and then a return flow going through the North Atlantic deep water that brings back the water to the south. And by doing that, it is also bringing heat, a significant heat flux to the northern hemisphere and to the atmosphere. So this is a cross-section of the temperature of today in the Atlantic from south to north, where are represented, in fact, the isotherm. And at the same time, this thermohaline circulation can be summarized as with that budget, about 20 to 15 sphere drop, 10 to 6 cubic meter per second, at about 20 degrees, and then a return flow, or sinking in the Nordic seas, and then a return flow about the same size in terms of flux, with a much lower temperature. And if you make the calculation, you can derive a heat flux that is on the order of 1 petawatt, 10 to the 15 watt. And of course, we have many, more precise numbers on that, but just a rough calculation shows you that it is a significant amount. So any mechanism that is decreasing or even collapsing, in fact, this process will have a direct effect on the temperatures above the North Atlantic and on the surrounding continents. And this is what we see, in fact, with the Heinrich 1 event. When a lot of icebergs were released, there was a drop of the salinity, a drop of the density, so the sinking at depth was no longer possible. And as a parenthesis, which is quite important, is to realize that H1 is, with this drop, with this catastrophic collapse of the thermohaline circulation during several millennia, may serve as a very exaggerated analog for what will happen in the future for the AMOC. So this is just a recent review of something like 30 modeling experiments in the frame of the CEMIP5 intercomparison project, where Wegener et al. Has compiled, in fact, the different changes of the AMOC, in sphere drop, over the next century. In that case, it is not due to iceberg release, it is due to the effect of the greenhouse gas and on the hydrology. But clearly, the only good analog that we have in the past of a change of the thermohaline circulation is H1 and things that are more or less similar. And what you can see is that for the next century, we are not speaking about a complete drop of the AMOC, but clearly all the models, even if they don't have the same intensity of the AMOC, of the meridional overturning circulation, show that there will be a drop in the intensity, and clearly it has an impact, a regional impact on the temperature. So this is containing about 30 modeling experiments with different type of ocean atmosphere, full-fledged GCM also. What is good with the model is that it's possible also to look at what they predict in terms of the distribution of the temperature. So this is, I just took one example among many of this kind of experiment trying to mimic, in fact, the Heinrich one. So this is taken from the work of Manviel et al. In 2008. And what is shown on the left is a map showing the anomaly of temperature that is corresponding, in fact, to this drop of this collapse of the thermohaline of this meridional underturning circulation collapse in the Atlantic. And we can see that it has a direct effect, a cooling effect in the North Atlantic, but not only, it has a direct effect also on the cooling in all the high latitude bands of the northern hemisphere. This is compatible with what we have seen with the work of Shakun. And we can see also that in the southern hemisphere, just because the heat was no longer transported northward, there is a slight seesaw warming that is spread over the southern hemisphere. This is clearly what we see also with the synthesis of the data. The other thing that is quite interesting with the model is that they consistently, when they do this experiment showing a drop of the AMOC, is that there is a robust shift, a southward shift of the Earth thermal equator, the intertropical convergence zones, the ITCZ. And coming from the same experiment, on the right panel, you can see the anomaly of precipitation. So in red, you have higher precipitation, and in blue, you have lower precipitation. And represented as stars, and the whole thing is corresponding, in fact, to a southward shift of this rain belt that corresponds to the ITCZ. And what the stars are corresponding to different sites where we have paleoclimatological information to show that it was indeed the case, that there were changes. And as you can see, the evidence is more or less compatible. There are only a few sites where it doesn't match. But at a global scale, we can see that it's more or less compatible. Now, there is an additional twist of complication. And I will try to now, this is to convince you that there is even more information that we can gather for this time period by looking at even more details. During this Heinrich 1 event, or sometime it is referred as the oldest dryas, or by George Denton and Wally Broecker as the mystery interval. So it is more or less what we are speaking about, this 3,000-year kiloyear period. So I will make just a rapid, I don't have time, in fact, to show you in details all the information, but I will try to illustrate a few of the recent information that were gathered not only by us, but by several groups on the fact that this 3,000-year period is even more complicated and probably more interesting than we think. So this is, we are starting with the tropics. These are a few records. Again, with the time progressing from right to left. The Cariaco Basin is an anoxic basin off the coast of Venezuela, and it is recording, in fact, the wind strength of the trade winds. So we can see that the Heinrich 1 time period, this 3,000-year period, is quite complicated. We can see that also from the recent work that was obtained in the frame of the ICDP drilling of Lake Petenitza by the team of Dave Odell, that that this Heinrich 1 period, this 3,000-year period, is corresponding to a dry period based on the ostracod of delta 018, the delta 018 of ostracods, and many other information, gypsum in the record, and so forth. But so it was composed. This 3,000-year period is characterized by two phases of dryness, and they are interrupted by a wetter period in between. So this is one confirmation in Central America. Further north, we have the well-known record of the pluvial lakes in the southwestern US, and so this is a representation of the lakes at their maximum extent. Especially, I mean, these are lakes that I mean, today the remnant is the Great Salt Lake, but during the glacial period, and especially during H1, this was the last decade of work on that topic has shown that the high stand are corresponding precisely to this 3,000-year period. The Lake Bonneville and the Lake Launton were much higher than today. So it was, in that case, a wetter period in that higher latitude. And there were many more lakes than the Lake Bonneville and Lake Loughton. They were, I mean, as you can see on that graph, taken from the work of Munro in 2012. And what these authors and others, like Wally Broeker, showed that this dry period was more complex and was, in fact, composed of two phases, one that was drier and another one that was wetter, again corresponding more or less to what we have seen of Portugal. A quick tour just to show you that now we are moving a bit farther east with a cave delta weighting record in a speleothem by Asmeron et al., showing that there were large swings of the precipitation of the moisture in New Mexico. And in that case, again, during the time period of this 3,000-year period, it was affected by different swings of the moisture level. And we have also information further north from with work on fossil dunes and paleosoils that were also indicating a dry period, but the dry period, again, is more complicated and is composed of two phases. Actually, I took directly those pictures from the recent paper by Wegener, who showed that they could identify H1A and H1B within, in fact, the sediments and within the paleodune record in the US. Again, I see that time is flying, so I don't have time to describe the ideas that are behind that. But these authors are trying to make sense out of the seemingly conflicting information. On one spot, it can be drier, and on another one, it is wetter. I mean, everything has to do with those northward and southward shift of the ITCZ, but not only. In fact, what they showed also is that it was affecting also the higher latitude, and especially probably it was affecting the position of the polar jet stream that explained, in fact, the change of the storm track and the rainfall in the northern US. And this is how these authors are explaining this connection between the ITCZ and the polar jet stream. Again, linked ultimately to the two phases that we have identified of the Iberian margin. We move now to another part of the world with the African and Asian monsoon area, where, again, over the last few years, there were many evidences showing that the Heinrich 1 event, this extended 3,000-year period, was very dry. So I took this picture directly from the review work of Steiger et al., who mapped, in fact, the different sites where you can identify a very dry period. And I even borrowed, in fact, the title, which is self-explanatory, catastrophic drought in the Afro-Asian monsoon during Heinrich 1 event. And you can see that the drought was widespread. You have a few spots, for example, in northern Australia where it was wetter, probably because the ITCZ was directly on top of that spot. But on most of the area, it was drier, and especially in North China, as shown, in fact, by many cave records, speleothem records, delta weighting records are in speleothem, in stalagmites, and especially in the famous Hulu cave at about 32 north. So here is just the glacial part of this record that is showing, again, a drop of a dry period during this 3,000-year period. I borrowed, in fact, this graph not from the original publication by Wegener, but I took it from the review paper by Broeker and Putnam, who tried to make a link between the complex phases within this 3,000-year period with the southwest US pluvial lake records. In fact, they were correlating the two phases that are evident in this Hulu cave record with the big wet and the big dry event that they were trying to identify in the US. So again, it stresses the fact that Heinrich 1 was probably much more complicated than we thought before. We are trying, in fact, to add new data, especially as you have seen in northern Australia. There was one point characterized by a wetter period, so we tried, in fact, to go a little slightly further north. In that case, this is just an illustration of one particular data set that we just generated recently. We took a core in the Gulf of Papua. During the glacial period, New Guinea was connected to Australia, and the site was collecting a lot of water, river water coming out from the Fly River. That is a major river and that was even larger during that time period. And these are the records that we generated recently, which are showing, again, large changes of the terrigenous input, and also we are using organic markers that are more or less linked to the fluvial discharge. Again, I don't have time, in fact, to explain to you all the details. We have a long-term trend that is probably linked to the fact that the core site is increasing its distance to the coast during the fall deglaciation, because the sea level is rising. But at the same time, we can see that the Younger Dryas and the Heinrich 1A and 1B are characterized by a higher flux that shows that the area was probably wetter during the glacial period, during the Heinrich 1A and 1B period. So when we make a summary of where there is evidence for this two-phase period of Heinrich 1, we can see that it's widespread. So I borrowed, in fact, that map directly from the review of Breuker and Putnam, and I just updated it with a few more points. And we can see that even if it can be complicated, for example, there is an anti-correlation between the moisture level between the tropics and, for example, the southwestern US, there is a correlation and a coherent picture that is linked, in fact, to the movement of the ITCZ and probably the polar jet streams. And ultimately, everything may have something to do with the release of icebergs in the North Atlantic coming out from the ice sheets of the time. I mean, we have to care also about the release of the Antarctica ice sheet also over the last deglaciation. That's another story that would be complicated to tell in a few minutes. But clearly, because we have identified the two phases with the IRD, probably the part of the answer of this complexity within H1 is coming from the release of ice from the major ice sheets that were present during that time, the Laurentide ice sheet on Canada, the Fennoscandian ice sheet in Northern Europe, and the Antarctica ice sheet that had also a deglacial history. So this is remaining work for the next 5 to 10 years, but what we need is a series of cores that are taken around all those ice sheets just to document, in fact, the flow of fluvial discharge coming out from the ice sheet. And just as a last illustration, I would like to show you a recent work that we just published, in fact, yesterday. So it came out in PNAS. It's, I mean, we are interested, in fact, in the deglaciation of the Fennoscandian ice sheet. And a few years ago, we published a record that was collected directly from the river, the Channel River that was collecting, in fact, the western drainage of the Fennoscandian ice sheet. And so yesterday, we published, in fact, a new record for the fluvial discharge coming out from the eastern part of the Fennoscandian ice sheet by taking a core and studying precisely in the Black Sea. So this is the site that is represented on that graph that was collecting, in fact, the meltwater coming out from the Fennoscandian ice sheet and also from the Alpine ice sheet of the time. This is the main picture, or the main graph that is summarizing, in fact, the information during with a lot of geochronological constraint. We have a record of the fluvial discharge between 10,000 and 25,000 years before present. And what you can see is that during this 3,000-year period corresponding to H1, it was even more complicated than having two phases. Of course, we need to map that everywhere for all the ice sheets, but in that case, we have evidence, in fact, 4 main pulses of input from the meltwater. Actually, in fact, it was known before we came as red layers, but we went slightly farther in the interpretation by adding many proxies, especially the isotopes of nelium that allows us to fingerprint, in fact, the source of water and the source of the erosion of the terrigenous input in the Black Sea. So those 4 layers, this is a zoom of this 3,000-year period. What we have evidence, in fact, is that there were cyclicity, in fact, 400-year cyclicity with 200 years of phase of large influx of meltwater, then interrupted by very calm period during 200 years. And when we say 200 years, it's even possible to count. What is marvelous, in fact, in those sediments is that they are barbed. I mean, we can see seasonal couplets. So I don't have time, in fact, to give you a detailed description of that. But this is a NICS radiography of the sediment, and you can see that there are layers, and we can even study the IRDs that are coming every season. So we have a seasonal record of the output from the phenascendent ice sheet at that location. And again, everything is in the paper that just came out yesterday. But what we think is that probably the ice sheet front, the phenascendent ice sheet front, was behaving with two main states. One that was during the calm period, these 200 calm periods with only surface melting, with retreating glacier that was frozen to bottom. And there were other phases that were more active with a proglacial lake that we know where it was. It's called the Lake Disna. And from time to time, there was a collapse of the ice sheet front because of, it's well known, the basal lubrication. And probably it was releasing a lot of bergs and meltwater into the river system. And this is what we see at the end in the Black Sea. So this is our thinking about the whole thing. Of course, there is more ingredient. It was behaving like a Japanese fontaine, but look at the paper if you want more interpretation on that. I would like to leave you, in fact, with a few take-home messages after this review from the big picture to the very detailed picture of the last glaciation. The first paragraph is just recapitulating, in fact, what a simple-minded summary of the last glaciation. So we know that the initial kick was the insolation linked to the orbital theory, and it started the deglacial process, but the whole thing was amplified by the CO2 that came out from the Southern Ocean. So we know that now quite precisely. And, but the ocean was not only important because of this CO2 degassing, it was also important because the circulation was affected, and this is responsible, in fact, for the gradient in temperature that we see here and there on the Earth. The other thing that is even broader in terms of importance, the last glaciation also teaches us that transient regional cooling can delay and mask a long-term warming evolution. Such as, we can see that for H1, we can see that for the Younger Dryas. It's clear that the Magdalenian prehistoric people that were living in France or in Spain, when they were seeing, in fact, this armada of icebergs coming on the coast, they were not thinking about living in a time of global warming. But they were, in fact. They were living during the last glaciation, and somewhere else it was rising in temperature, and when you take the global mean of temperature, it was rising smoothly over the full deglaciation. So the analogy with the present-day situation with the present global warming is not direct, but this kind of information is quite important also to keep in mind. And the last broad statement that I learned, in fact, from the study of the last deglaciation is that the small picture is as much interesting as the big picture. I could have started, and we could have stayed, in fact, with the initial picture, with the smooth deglacial process, since we had with CliMap. But clearly, we learn much more by looking at the details. And I think this is a unique aspect of the climate system to be so different at the different scales. In fact, when we look, I showed you that when we look precisely at seasonal bands in the Black Sea, we can see a process that is the dynamics, the internal dynamics of an ice sheet. And at the other end of the spectrum, when we look at slow variations, we are looking at the orbits, at astronomy. And in between, we can look at the carbon cycle, we can look at the ocean. So a wide range of process when we look at the different timescales. So clearly, the small picture is as much interesting as the big picture. So thank you very much for your attention.
Thank you very much. I understand Edouard will be happy to take questions. Yes? Please, can you? You have not?
Okay, I should.
This was wonderful and rich and great, and thank you. But the difference in the precessional cycle, with 3,000 years, is the same as essentially between the equinox and the solstice. Okay, it's 1/4 of a period. Mm-hmm. So I somehow lost between the beginning, when you showed us that picture from Milankovitch about how this is just the right time for deglaciation to occur. If you now shift it by 3,000 years, it is just the wrong time for deglaciation to occur.
No, I mean, if you look at the insolation at 65 north, it starts to rise much earlier than that, much earlier than the middle of the last deglaciation. Actually, 30 years ago, with the LGM at 18K, it was a real big problem in the community. In fact, adding 3,000 years really solved part of the issue because it was closer, in fact, to the beginning of the rise of the insolation. The insolation is starting to rise at 25 to 26K, in fact, in the case of 65 north. So I'm not speaking about the maximum. The maximum is at about 11,000, so it's really at the middle of the last glaciation, which is important. But the early start of the insolation rise in the northern hemisphere is starting much earlier than even what we know today about the last glacial maximum at 21K. 18K there was a massive lag to be assumed, and this was really creating a problem at that time. This is what I remembered, in fact, from when we added, in fact, these 3,000 years.
Okay.
I don't know, maybe André Berger or other specialists could comment on that, but my impression is that adding these 3,000 years has gone towards a better and an easier explanation for the entire deglaciation.
Okay, thank you very much. More questions? No? If not, I would like to thank you for being here, for your attention. I would like to just thank the speaker. And we will have an award ceremony this afternoon. So I would like to invite you at 5:30 in this room, where we'll hear more about our medalists, including Edouard. Thank you very much.
Okay.